So I'm so excited to have Heather Schijns with us this week. So Heather is a Global Principal Geoscientist at Seismic Geophysics at BHP's Resource Centre of Excellence Group. She has experience in North and South America, Europe, Australasia and Africa for a range of commodities, including nickel, copper, lead, zinc and coal. So it is going to be wonderful hearing her insights on effective mineral exploration using seismic methods. And yes, thank you so much, Heather, for joining. It's just wonderful having you.
Well, thanks so much. I'm super excited to be here, and I know it took a while to kind of organize. I'm especially nervous now because you guys have all learned that I know nothing about the Blue Mountains. So next up, you're going to see how much I know about seismic, but I guess that's how it's going to go today. So I guess thanks also to Cam, because that was super. Like I said, I learned a lot and learned how much I didn't know. But anyhow, on to my presentation. So this is about effective mineral exploration using seismic methods. And I thought it would maybe be interesting to kind of think about what effective meant to begin with. So that's kind of where we're going to start today. Is I'm going to have a bit of a razz of my fellow mineral exploration geoscientists, because when you compare us to oil and gas, I mean, it's hard to argue that we're very effective at all. So fair warning, I've compiled a bunch of statistics and made some beautiful charts in this presentation, but take them all with a grain of salt. They're compiled from many sources and then spliced together in ways that are probably not apples to apples comparison. But I've done my best to give us a bit of a picture here. And so for oil and gas, as best I could put together, their discovery costs were about 375 million for a field. And then for minerals, Richard showed at Minex Consulting has done amazing work in actually compiling all these stats, and he says about 185 million for, I think, base metal deposit. In terms of how, so I guess, you know, the prices are not that different, right? I mean, oil and gas is about double, but it's not off the charts different in terms of their discovery costs. When we look at how they make that discovery, that's where we start to see some really big differences. So in terms of their expenditure on geophysics versus drilling, we see oil and gas spends nearly the same amount on geophysics, which is the orange part of the pie, in case you couldn't guess. Whereas minerals, you know, it's something like 10 or 20% there. You can see it's very small. We do a lot more drilling, which is interesting because when you look at our success rates, again, put together by Minex Consulting there, but 1 in 6,900, that's for gold deposits, I believe. 1 in 6,900, I ran out of room trying to show the number of holes we drill that find nothing, versus oil and gas, they're about 1 in 2 in mature fields. And that's actually being a bit pessimistic. You read some of the press releases and they're saying they've actually got 100% success rate now, and not only that, but able to sterilize some of their areas that they previously thought might be prospective. So very dramatic difference in terms of actual effectiveness of seismic and geophysics in general in oil and gas versus minerals. What I want to talk again about the effectiveness of geophysics in general in mineral exploration. And a few things, kind of, I guess, thought experiments on this slide. But again, we're all fairly familiar with this graphic on the left, I think, showing that in general, this one's specific to copper, with the circles kind of denoting the size of the discovery. And then on the y-axis, we've got the depth of the deposit, or to the top of the deposit, and the year on the x-axis here. So what we can see, and I think we're all well aware of this, is that as time has gone on, many of our discoveries are starting to come from a bit deeper. Back in the past, things were easy. People would stumble across deposits, you know, walking their dog or whatever. Everything was outcropping for those discoveries, or very shallow. Now we're starting to get stuff that's down, you know, 100, 300 meters, and some quite a bit deeper. So that means that our cost of drilling, if we have to drill 6,900 holes to make a discovery, when they were really shallow, that was cheap, right? But as we go deeper, that starts to be a lot more expensive. So this is kind of what this graph here is trying to demonstrate. And again, like I said, we're kind of thinking thought experiment here. Obviously, at very shallow depths, your cost of drilling is never zero. But if you don't have mob demob, if you just forget about that, right, you're purely paying by the meter for your drilling. As you go deeper, it's a very linear relationship, right? You've got to drill X number of meters to get to depth X. Whereas geophysics, our costs are actually decreasing as we're looking deeper, because typically, as we're focusing on deeper exploration, we can actually increase our line spacing or decrease our station spacing. And so we actually have to take fewer measurements if we're just trying to image deeper. So because of that, and again, not getting too fancy about this, but your costs decrease as you start to go deeper with the actual method and acquiring that information. If you start to look at the actual NPV of your discovery, obviously at these shallow depths, if your cost of drilling is it's basically nil because you're only drilling 1 or 2 meters in this thought experiment, you're capturing the max NPV with drilling. Whereas if you do geophysics and then need to still drill, you've increased your costs substantially, but the NPV of the value of your deposit is the same, right? So your actual NPV is less if you bother to do geophysics at this super shallow depth. As you go deeper, if geophysics is really increasing your success rates, you're not drilling 6,900 holes in order to make your discovery. You're only spending a little bit on geophysics, and then you're able to do targeted drilling. Whereas if you're just grid drilling, you've got to drill all those holes, and it's quite a bit more expensive than it would have been to do geophysics and then drill. So which approach you should use to do your exploration depends on where you're expecting to actually discover your deposit, right? If it's going to be shallow or deep. And turns out for seismic, this makes a big difference too. So I talked about how all geophysics gets cheaper with depth, but specifically seismic very much gets cheaper with depth. So what we're looking at here is these circles are kind of proportionally sized to the cost per square kilometer of 3D seismic. And the yellow ones are the cost for minerals deposits, and these again are just from the public domain, so not necessarily, some people may be doing better, but not actually publishing that information. But we'll use it as kind of again, just an estimate. So, and these are the years, okay, of when these surveys were completed. And we'll see that becomes relevant in a couple slides. So in general, our minerals deposits or our minerals seismic is costing something like 100,000 to 200,000 per square kilometer. Whereas petroleum, for whatever reason, is costing sometimes as low as $3,000 per square kilometer, and up to about 50,000 in this estimate. So really big difference, and part of that is that petroleum's doing larger surveys. They're amortizing the cost of the mob demob over a larger total area. But the big difference is that line and station spacing, and that has to do with the depth of investigation. So doing a mineral seismic survey is a lot more intensive in terms of amount of data you have to acquire, because we tend to be looking very, very shallow, so sub 500 meters, whereas, as a general rule, petroleum is looking quite a bit deeper. So theoretically, we would think this is kind of good news, right? We're looking deeper or that's where discoveries are being made, is deeper, and geophysics is cheaper when we look deeper. So this is great. The problem is we have to think also about the reliability of our geophysics. So again, I've kind of bastardized some of Minex Consulting's work again here. Obviously, discoveries are made not just by drilling in geophysics, right? Some of them are made from conceptual geology, from geochem. I've just looked at the ratio between discoveries that are made primarily from drilling and discoveries that are made primarily from geophysics. And Minex Consulting separated these by depth. So we see that in the top kind of 300 meters, many more discoveries are made with geophysics than they are by just randomly drilling, grid drilling. When we get below 300 meters, all of a sudden we get this massive jump in the amount of successful discoveries that are made by drilling, and a comparative reduction proportionally in terms of how many are made from geophysics. And so this speaks to the reliability issue of geophysics. So drilling, as we go deeper, you're getting the exact same product, right? A piece of core that you can send an assay and figure out how, and do your geochem and figure out how close you are to a deposit, or if you've actually hit a deposit. Geophysics, as we go deeper, becomes less reliable. So particularly if you put the same deposit deeper and do a magnetic survey over it, for instance, it may start to fall below the signal to noise level at depth and become indetectable. And this is what we see, right? Is below about 300 meters, people can't use geophysics to make the discoveries as efficiently. So this actually changes our NPV relationship once you consider the fact that geophysics isn't reliable as you get deep. So as before, when things are super shallow, you again end up with this really simplistic model where your drilling is ridiculously cheap, nearly free, because you're paying by the meter only, versus your geophysics was quite expensive to acquire. It's reliable, so you're doing well, but it costs you so much to acquire that your total NPV of your discovery is less than if you'd just gone ahead and drilled it with your basically free drilling. Then we get this kind of sweet spot here, and I'm not going to get too specific about what depth range that is, but the work kind of speaks for itself, that it's maybe in that 100 to 300 meter range that we get this bump over the cost of just drilling things. And that's where your geophysics it's reliable. It's not that expensive to acquire, and it's actually saving you the amount of drill meters that you're having to drill, because it's allowing you to prioritize where to target. Down at depth, though, geophysics costs you money, not too much, but it still costs you money to acquire, and it's perhaps useless, right? That's the worst case scenario down at this very far depth. You paid for the geophysics, it didn't help. Your success rate is exactly what it would have been if you'd just drilled. So you're actually, again, below the NPV line of where you would have been if you just drilled. And the terrible part is that, as our discoveries get deeper, both of these show that our NPV is going down. So this kind of sucks, to be blunt about it. And we actually, if we want to be effective at our mineral exploration, we have to move this line if we want to effectively use geophysics. So we either have to move it straight up everywhere, by changing the cost of acquiring the geophysics, okay? Or we have to change this curve and actually make our geophysics more reliable. And not just the geophysics itself, but the interpretation of the geophysics. So, well, sorry, I guess I'll talk a bit more about this, but the issue, right, even if we reduce the cost, we're still not really up where we want to be. We're probably not in this upper right quadrant, which would be the ideal, right? So I'm going to talk about reducing the cost, and that's what people always focus on with seismic, but we actually really have this problem that we need to improve the reliability. And I think oil and gas speaks to that so effectively. Their success rates are so much higher than ours because their data that they're using is more reliable for them. Now, I'm not saying that we have to copy them, but we have to copy that thought process. So we'll talk a bit about cost and how that's actually been reduced in the last few years. If you'll recall, I showed some costs for hard rock seismic, and I think the latest one there was 2016, and I don't think it used this new nodal technology, but I'm not totally sure. Don't quote me on that. But we didn't see costs from the last couple of years for sure. So in 2015, 6 autonomous geophone nodes, so seismic receivers, were introduced to the market, and that was the first time that we had nodal technology. Before that, you can see in the bottom pictures, everything was cabled. And you can imagine that the manpower just to distribute these cables, to carry them around in the field, you needed more trucks, you needed more people, you needed more time. So the fact that we have these nodes, and you can see some of them are very small, very lightweight. It's been a 20 times weight reduction compared to cabled geophones, 80% fewer vehicles, obviously massive increases in productivity. Areas that you can get, going across a road with a cable was a logistical nightmare before. Now with the node, it's very simple. So increases in areas you can access, and a reduction in things like manual handling, environmental impact, etc. So this has been a major driver of reduction in cost in seismic acquisition. The other aspect that's really changed in the last few years in the hard rock space has been simultaneous sources. So I've shown a bit of this at a presentation for an EHE workshop. So if you've seen it already, apologies for that, but we'll go through it again. To talk about how simultaneous sources have affected seismic reflection acquisition, you have to understand a bit about how seismic's acquired on the field. So in general, and not every survey, but the most common one is an orthogonal layout. So you'd have, in this case, all these vertical lines would be maybe your sources, and then all the horizontal ones would be your receivers laid out on the ground. And this would be your full survey area you were trying to cover. Now, you wouldn't have all of your receivers out at once, because that's very expensive and there's limits to how many are actually available on the market. You would lay out what we call a patch. And then you would put your seismic source, and you would actively read only on some portion of those geophone receivers that were on the ground. So these dark black circles would be your receivers that were active. The blue circle is your seismic source, okay? And you would do this with multiple seismic sources on the ground at the time. Your seismic source in this scenario is a Vibroseis truck, because they're the typical one that's employed these days. People don't tend to like to use dynamite. So you would have this Vibroseis truck put in its sweep into the ground, which is the seismic source, and then it would move to its next survey location, okay? And then after it finished, you would have another truck in a different area, with a different number of receivers active around it, and it would do its signal into the ground, and then it would move. Then you'd go back to this first one you had, and it would do its next measurement, okay, and move to its next location. And each of those signals, the Vibroseis makes a signal that's kind of the sinusoidal waveform, and it makes that signal typically in mineral exploration something for 8 to 30 seconds, and then we listen. We listen for the seismic source to bounce off whatever it's bouncing off, or target, hopefully, down in the ground, and back up to the surface. So ultimately, this second panel is what we record on our receivers, and we correlate that. We correlate it, and we get this correlated record. That's the length of the listen time, which is usually 1 to 3 seconds. Okay, and this correlated record is the equivalent to what you would get if you did use an instantaneous source like dynamite. Okay. So if you use flip-flop acquisition, which is up to a few years ago what was most commonly used, what would happen? You would have your seismic sweep, then you would have your listen time here, and then the next truck would start its seismic sweep, okay, straight away as soon as that listen time was done. And then it would have its listen time, and so on. Okay, so that all the time, there was always a sweep happening. This would be your big long record you would get continuously, but you would correlate it, and you would get one record here, and then this gap in time of that 8 to 30 seconds before your next record happened. Okay, that's when we separated in time. There's another way you can do this, though. You can separate in frequency space, and this is called slip. And so to do a slip sweep, your first truck starts and makes its seismic source. After the slip time has elapsed, the next one starts. This first one's still going, okay, and it's going to have its listen time after that, but the second one has already started. But because the frequency content when it starts is different from the frequency content of the first truck, when we correlate this, we actually get two separate records, and they're right back to back against each other. Okay, so we've saved ourselves heaps of time because we're not having that big dead time in between our seismic records. So this sounds way more efficient, right? But this is actually 1991 technology, and at BHP, we didn't acquire our first simultaneous acquisition until 2018. And we were amongst the first to do that in a minerals seismic survey. So simultaneous sweeping was actually identified or first developed in '79. Flip-flop, which was most commonly used for hard rock seismic until about 2018, was developed in '91. Slip sweep was developed in '96. What we tried in 2018 is this distance separated simultaneous sweeping, but they actually have ones beyond that. They're using random sweep now, which is even more efficient. But using distance separated simultaneous sweeping, or DS3, with slip sweep, that acquires 10 times more source points per day than flip-flop, and 20 times more than if you only have one vibrator operating, which for many of our seismic surveys, which are small, they only need one vibrator. And so it's heaps more efficient, but we only recently started doing it in hard rock settings, or in mineral settings, I should say, because we're doing it in coal at BHP. But the difference is really striking. And so these are the stats from our first survey that we did in 2018. We've refined it since then. But initially, we were doing flip-flop acquisition. In practice, like I said, that would be 0 seconds between when the first record ended and the next Vibroseis truck would start. But in practice, it was about 4 seconds. So this is kind of the histogram of how much time we usually had in between. When we started using DS4, so it's DS3 with the slip sweep, we were able to start the sweep 8 seconds before the one before ended. And so for a 20,000 shot survey with 20-second records, it's actually halved the time of acquisition. So it would have been 13.3 days using our conventional acquisition techniques, but using simultaneous sweeps, we reduced that to 6.7. So we estimated it saved at least 50% of the acquisition time. And lest you think that this actually was deleterious to the data quality, because we had such savings, we could actually increase our signal to noise by 30%. So this is the raw data on the left. For those of you who don't know seismic, this looks perfectly normal once it's been deblended. And this is the 3D from the DS4 acquisition, and then a line through the same area that was acquired with just single Vibroseis. So you can see at our target horizon, we're actually getting much better results, and we've had a 50% reduction in how long it's taken us to acquire it. So in terms of cost, seismic in the last 5 or so years has become so much cheaper than it used to be. So that leaves the issue of reliability. And in that side, there have been a lot of really big changes too. So what a lot of people don't realize, I certainly didn't before I started looking into it, was how much global computing power is actually taken up by seismic processing. I saw a stat where they said something like 70% of the total processing power globally was seismic. I think that was pre-Bitcoin, so I don't know if that's changed. But just to give you a sense, so this is supercomputer processing power in gigaflops. I don't know what those are, so don't ask me, but a unit of processing power, and then versus year here. And you can see it's a logarithmic plot on the y-axis, and this has been increasing fairly steadily over the years. So the orange is the #1 supercomputer in the world, how much processing power it has. Yellow is the number 500 supercomputer in the world, and blue is the sum of the top 500 computers in the whole world. So in 2014, this is from Chevron, they started introducing in their processing flows what's called acoustic full waveform inversion, or FWI. And you can see that the processing power needed to do that is at this black line. So before 2005, I mean, you could have put a few supercomputers in parallel, but even if you had 500 of them, it wouldn't have been enough. So this really only became feasible technology in the last couple of years. You can see some of these seismic processing companies where they sit on this graph. Okay, so CGG is the #2 company in the world, and they had the equivalent processing power of the #1 supercomputer globally. And Total is, I think, not even top 5, but it's still right up there, right? So the processing power that these seismic processing companies have is just astounding, and some of the stuff they're doing is literally pushing the limits of our total ability in the world. And you can see that reflected in their actual algorithms here. So this is a quote from Intersect 360 research. But oil and gas has the highest overall rate of internal software usage, more in-house applications and algorithms than any other commercial sector. Why is that? Because there's so much importance on having efficient algorithms when you're really at the limit of your processing capabilities. So what can we do with all these in terms of reducing our costs and improving our reliability and the effectiveness of our exploration? So with our reduced costs, we can have more measurements on the ground for the same price point. We can have a richer distribution of ray paths through the earth, right? And by having more unique measurements, that's really effective for increasing our signal to noise and increasing the reliability of our image. With the increased equipment availability, we'll talk a bit more about this in a second, but that allows us to actually put on the ground seismic survey designs that allow full waveform inversion, or FWI. With the more processing power, we can process more measurements. Okay, first off, so that's great. We can actually improve our interpolation as well, and that's really important for when we're trying to, correct for lines that weren't quite straight or decimate our data perhaps, so that we can actually reduce our costs and acquire fewer measurements. We can actually do full waveform inversion. Like I said, we're right only in the last 2 years able to do that. And another one that we haven't talked about yet, but we will in a second, is improved migration accuracy. So we can actually put our seismic measurements spatially into the correct place with more accuracy. So one of the unique issues we have in hard rock is steep dips. So this has been one of the issues in terms of getting high quality data in hard rock. We got a little schematic. I'm not going to ask you guys to do the math, but for a reflector, so your target horizon is dipping 70 degrees. Your seismic ray is going to impact that perpendicularly, okay, in the ideal scenario here. So to look 1 kilometer down, you actually have to measure nearly 3 kilometers away, so 2,700 meters distance, okay? And what that means is we typically have an area we're actually trying to image, right, our target area, but with seismic, in order to image it, we have to step and measure all around that as well, so that we can get these ray path angles, we can get the geometry for our acquisition. So just looking at this example, if we're trying to look 1 kilometer down, which is pretty normal goal for a seismic survey in minerals, you need 3 kilometers on either side, up, down, side to side, okay? So you need 6 kilometers by 6 kilometers, basically, and you still don't have any appreciable image area, but you've got a 36 square kilometer survey. So let's look at how many surveys globally have actually even managed this geometry, okay? And again, just pulling from the public domain stuff, so I'm sure there's people who've done bigger and better things out there, but plotting what's out there in the public domain year against area of survey, most of them are kind of at that kind of 20 to 40 kilometer mark. We've got a few outliers, but not too many. So when we look at how many people have effectively been able to image these sorts of dips, it's basically no one over any kind of area. And the food for thought here is that your kind of border that you need around your image area, it doesn't change in size if you have a particular dip, right? So it's not dependent on the size of your image area in any way. It's static. So if you're doing kind of a 1 square kilometer image area, then you've got, 6 kilometers this way, 6 kilometers that way, 6 kilometers up, 6 kilometers down, or sorry, 3. I should have said 3 there. Sorry, guys. But you've got, something like 36 square kilometers to image 1 square kilometer. Whereas if you start looking at larger image areas, the amount of dead space that you've had to survey over is proportionally much less. Okay, so here we're looking at your total survey area versus your image area, the ratio. And you can see as we start to have bigger image areas, this is much more effective. The stuff you're surveying is actually stuff you want to be surveying, which is good news. The other thing we talked about for reliability is this idea of interpolation. So that's been a really big change in the last few years, is our ability to interpolate data better. And I'm just showing you an example here of this is looking at 2D data here, and then they've applied 2D filters onto it. So in order to remove noise, you often have to predict the noise, right? Which is where interpolation comes in, even sampling, etc. So if we interpolate just in 2D, this is about all we can do in terms of noise removal. Again, I know a lot of people may not be super familiar with looking at seismic, but if you keep your eye on this first break, for instance, which is our refracted wave, you can see we're not really getting any gains in terms of the signal there, okay? If we look at doing 4D interpolation, and there's actually 5D and 6D, so they're not very good at their dimensions in oil and gas. They just keep going beyond reality. But we can see that improving these interpolation algorithms using more dimensions and hence an increased processing cost. Again, if we look at the first break in this raw data versus if we use a 4D technique to interpolate it, I mean, it's a dramatic difference in recovery of that signal. I was talking about full waveform inversion because this is another way that we can get really high quality images now that we couldn't do a few years ago. And this is both about processing power and the introduction of easier to deploy seismic receivers. So if you're looking at a cross section, full waveform inversion uses reflected waves and diving waves. And here you'd have a source. You'd have a source here, and you'd have a source here, and a receiver here and here. Okay, and you would measure these reflected waves off this interface. Diving waves take advantage of this gradient in seismic velocity that actually bends the ray around. Okay, and so here your source is here and here, but your receivers have to be much further away in order to acquire those diving waves specifically. So most reflection surveys, as you can imagine, focus on the reflected waves, which requires less actual equipment on the ground. To get the diving waves, you've got to have those near receivers to collect your reflected waves, but you also need to get your diving waves over here. And that distance is usually in sediments. It might be, if this depth is 1, you might need 4 times that in terms of your distance between your sources and your receivers. In hard rock, that ratio might be more like 5, 6, 7, 7 kilometers to 1 kilometer of depth. So again, let's look at kind of what's out there in the public domain for global hard rock seismic surveys. Maximum offset distances, and most of them have been below 4 kilometers, which is in a lot of hard rock settings only going to get your diving waves down, 500 or 600 meters, which isn't going to help you do full waveform inversion below that. Why do we care so much about full waveform inversion? Here's an example from some work BHP did in the Gulf of Mexico. They had acquired a survey conventionally, and it didn't have those long offsets over a decade ago, I believe. And they processed it, I think they reprocessed in 2014. I don't have it in front of me though, but this was the best quality image they could get with the latest processing at that time. They went back, they reacquired with longer offsets in order to do full waveform inversion specifically. And in that same area, identical area, this is now the image, okay? And so not only do you see the image quality itself is much better, but you can see the interpretation has changed fairly significantly with, again, that impact on how reliable is your geophysics when you're trying to drill a specific target. And then we talked a bit about migration as another aspect of improving reliability of images. This is a really simple example of 2D versus 3D migration, but there's also different types of migration. There's time migration, there's depth migration, there's pre and post stack, and then various migration algorithms like RTM and Kirchhoff. It's a whole thing, but let's keep it really simple and just look at 2D versus 3D. These are in the same area. This is an example from Escondida copper mine down in Chile. This is the area processed in 2D and then obviously migrated in 2D. And then that equivalent section processed in 3D and migrated in 3D. And you can see again, just a dramatic difference between the image. And this is, I think, where we need to start to talk about not just the quality of the seismic image when we're talking about effectiveness and reliability, but also how we're actually using these images for exploration. And I think a lot of geophysics is used very empirically for direct detection, right? We're drilling the mag highs, we're drilling the gravity highs, or the EM conductors, or whatever. And there's certainly conceptual aspects to that, but we're effectively direct targeting. With seismic, we're probably not going to have a seismic reflector associated with a lot of our deposit styles. So gold, disseminated deposits like porphyry at Escondida, we're not going to be able to direct detect that mineralization. So we have to use the mineral system, and certainly oil and gas is in the same spot, right? They're not direct detecting their oil. If they were doing that, they'd be drilling every reflector, which is not going to be very effective. So we have to use the mineral system. Cam McQuaig's one of my managers, so I have to show his theory here. But there's 5 key elements according to Cam. So deposition, preservation, architecture. We need a geodynamic trigger, and we need fertility. And seismic can actually help us image some of these aspects. So looking back at that Escondida slide again, this is the seismic, but let me put the interp on. And you can see the structure. And this was clearly interpreted off the 3D image here, not the 2D, but what you can see is this kind of flower structure here, okay, this kind of tulip shape that we have. And that's actually an extensional or transtensional structure. So that's actually our geodynamic trigger in action. That's that extension happening that allowed fluid to flow up from depth and transport to surface. We've actually got the architecture here too, because we can see we're going quite deep with these structures. And that gives us a vector, right? So we've got some architecture here. We've got the geodynamic trigger that we've imaged. We're not speaking to the fertility here. But seismic isn't meant to be a standalone method, but it's given you 2 important pieces of your mineral system to help with your interpretation. And in 3D, the other thing we could see, these are just 2 identical panels, okay, but the right one has the interpretation on it. So just slicing through at various depths from surface. And on the right, you can see the actual porphyry stock that we imaged. And then the little green dot is the magnetic anomaly that's associated with that porphyry stock. And I think we can all agree that that sort of tiny anomaly might not get drilled on its own without having these other contextual elements of the mineral system. So my summary, effective use of seismic and mineral exploration will benefit from reduced costs. Those have actually come down a lot in recent years. We've got simultaneous acquisition, we've got nodal geophones. If we want to reduce costs further, we need to look deeper or have larger surveys. Counterintuitively, our cost per square kilometer is going to come down that way. Cost is okay, but I think the bigger takeaway is that we really need to improve the reliability of our interpretation. So not just the image, there's a lot of advances that have been made recently in image quality, but also how we use that image, our actual geological thinking, our geological focus. We need to move more towards a mineral systems thinking and away from empirical detection if we're hoping to effectively use something like seismic. And if we do that, then maybe we can get a bit closer to that 1 in 2 success ratio that oil and gas has versus the 1 in 6,900. So this potentially could fundamentally change how we explore, but we really need to think differently. And that's all I've got. So thank you, everyone.
Thank you so much.